which holds 512 kilobytes of RAM. Can be used in a Model 2. Should be working in a Model 12, but I have never tested. And I came up with the board because it is possible to do it with current day or almost current day electronics. And with the original Tandy boards, you just couldn't reach that limit. So getting the idea and creating a list of requirements. The other thing that we'll be talking about is the Model 2 itself. How does it fit into the Model 2? What did I use for creating it? So KeyCut is one of the things we'll be discussing. And what did I do for the decoding electronics? We could go for TTL, which takes a lot of space and is not easy to change if you make a mistake. Or go for programmable chips, which is the GALs, gate array logic, which can be programmed with a cheap programmer. Then you need the boards to be made. I cannot make boards, so the Chinese can do everything, so they can also make nice boards for you at a reasonable price. Sourcing the parts is also a source story apart. And then assembly and checking, testing the board. Of course, also I make mistakes, so I can tell you about it, and you can learn from that. And then the final board. So I have a board here. I will show it later on. I have also some bare boards if somebody wants to make its own. My requirements, always, I try to make primary requirements and secondary requirements. So secondary is nice to have, but primary you should reach because otherwise it will not work. So it should connect to the Model 2 bus. It should take care of the video memory, so it should create a gap as soon as video is accessed by the Model 2. And it should take care of the boot ROM, and not in the way of the boot ROM, but fortunately that's already taken care of by the electronics on the CPU board itself. So you don't need to do anything special for that. Of course, 512K is too much for Z80 memory space. It can only address 64 kilobyte at once. And if you want to do more, you have to do page swapping or paging as it's called. And in the Model 2, that's arranged using a 4 bits on port FF, so the last port 255 in the system. And from that you can select any of the 16 64K pages. There are some limitations. Page 0, which normally is used by the operating system, you cannot map out. It's always in place. In the Model 12, that's different. There you can take it out and replace it with another page. I did not implement that here, but you could do it by reprogramming the GALs. And if you map page 0 to the upper half of the memory, so the upper 32 kilobytes, then you will end up with nothing. The emulator also will do that. Because that memory space is then used by the 68,000 processor memory boards. So even with the bare machine, swapping that page, you can test and have a look at the 68,000 memory. And at the reset, of course, everything should return to a defined state. Secondary requirements were connected to Model 12. I hope it works. I never tried it, so it's still an open issue for me. I did use port FE as a debugging board, so you can write to port FE and see what results is. There are some LEDs on the screen on the board, so I can check status. I can also show you the memory map bits and also port FE, so it's facilitating and debugging the board. And the other thing, disable use of page 0 and 1 for those who have an original 64K or 32K board in the system. You can map that out. So if you select them, they will not be using the new RAM. And the same for pages 14 and 15, where the lower 16K is used by the hard disk controller. So that's big. There's a display on it which shows you which page is selected, and there's an indication that video memory is active. So even if your system is running, it will have some blinking lights which will show what's happening. There's a test mode. When you reprogram the GAL, you say, okay, I just want to have I/O access in a regular Model 2, and you can test if the board works without using the memory that's on there. Custom GALs and securing possibility. Yeah, securing. As you can see, the board is quite small. It will fit in Model 2, of course, because that's the slot size. But you can, with the bracket, you cannot secure it. So it has two holes in there, but you can put it's called a strip, aluminum or a plastic strip, which can extend, and then you can fixate it. But if it's on a desk and it's not moving at all, then it will not fall out. It's sturdy enough, and it's not a heavy board at all. The Model 2 block diagram is in itself very simple. You have a motherboard. They call this motherboard. Normally, when you talk about computers and motherboards, it's a huge board filled with chips. Well, the motherboard in the Model 2 is just filled with slots, and that's it. So it's actually more like a backplane than a motherboard. You have a floppy controller, line printer interface. That's one board. You have a video board. You have a CPU board, and then you have a memory board. Normally 1 or 2, and the 32K was an option. I have never seen it in real life, but they do exist. Of course, the slots are, these boards only take already 4 slots out of 8, which means you cannot extend up to 512 kilobytes. Especially when you change it into a 68,000 system, you need a post CPU slot and a memory board. So that eats up a lot of space. By the way, if you have any questions, then just ask them now or ask them later. I will be here for all 3 days. This is the motherboard, or what I prefer to call the rear panel. Slot definition, so you have 80, you have the slots with 80 connectors. Mostly used for the Z80. What you can see here is 8 reserved, and those are the lines for the 16-bit data bus. Z80 uses 8 bits, and 86,000 uses 16 bits. And of course, when you build an additional board, it has to fit in here and does not have and must not mess up signals. So there are signals here like the interrupt lines. They should be daisy chained or whatever you want to do with the board. This is the schematic of the Tandy memory board as it is in the service manual. All these very similar chips are the memory chips. They are 16 kilobit piece, so the 16K times 1 bit, and that's what you need in order to fill up a full board of 64K times 8. Address decoding, this is the interface to the bus for the data lines, and the interesting part and the most difficult part is address decoding. This is the decoder that takes care of port decoding, and up there, here, there's a bunch of jumpers which select the address of the board. So you can say this board has page 0 and 1, or page 2 and 3, or whatever you want to do. And that's the thing. Of course, I will not do that in 512 because it can arrange everything, but then you have to take care that it will not mess up. Some more details. There's a list in the service manual on memory pages and how they can be selected. So a lot of jumper stuff. And that's the corner of the board which is doing that. I didn't bring a 64K memory board, but I'm sure they are here on the floor somewhere. This is what the 64K board looks like, and this is what my 512K board looks like. And this is same size, so same size of the connectors. And you see the components here is buffers for the data control and address. lines, so that's 4 chips. 2 with the yellow sticker for the decoding logic, so I can select the correct port and I can select the correct memory when needed. And these 2 are 8-bit latches for the I/O, so I can program data in there by out command, so I say out 55, and then it will store that. And then you have here 2 arrays of 10 LEDs each, which will show the data which is stored in these latches. So this one is used for the video, for the page selection, so it is needed. This one I use for debugging, and there are some spare lines over here which you can use to make connections if you want to see what the status of certain lines. As you can see, let's look upward from the board. Of course, if you have a model 12, then you would see nothing because it's a closed panel. But you could use an angled bracket, an angled slot where you can put your LEDs in and they look in this direction instead of upward. My first idea was I know nothing about what's happening on the bus, so I put in displays here which show me address and data lines. I put up displays here which show me the page used and everything in discrete logics. Nice idea, not flexible enough, so I said, well, this is not the way to go. So I abandoned this first design and came up with another design. Also, I was looking at how do I draw my schematics, how do I design the stuff, and looking at what's available. KeyCut is a very popular, very well-known tool. You can find instruction videos, a lot of information. And the other nice thing is you can make designs, you can make boards, and you can also make the files for the boards which can be sent to a factory that create boards for you. And so the factory I used in China, PCBWay, will do it, but also in the US there are many factories that accept a set of these files and make boards for you. My schematic looks a little bit different. Of course, on the far end, the bus connector, which I need for all the signals. My buffers here, which take care of separating the signals on the bus and the signals on the card itself. So without creating additional load doing that. And one thing it will also do, but that's my preference, when you look at the signals on the bus, they are all inverted. The data lines are inverted, the address lines are inverted. I don't like to work with inverted signals, so my buffers here are all inverting buffers, so I have the normal signal on the bus or on my card itself. That's my preference. You don't have to do that. You can also take another approach. Then you have this one and the top, that one, are the 2 gals. They take care of the address decoding, the signal decoding, the port decoding, and also they can. I'm using them also for allowing jumpers on the board, which can be read out. So if you put a jumper here, you will skip pages 0 and 1. If you put a jumper here, you will skip pages 14 and 15. And the large chip is, of course, the memory chip. Just one chip which has 512K kilobytes of memory, and it's static RAM, so you don't have to mess with anything on refresh signals, which makes it much easier to work with. On top, that's one and this one here are the 2 latches for the data, for the I/O ports, and these 2 are the LED arrays, which will show you the signal that's or the data that was latched in. Around here you see decoupling capacitors, and here 2 signals that are looped, so the interrupt line and the thing, so if you put the board in, it will not interrupt. anything. The component list in itself not too difficult. The buffers, first two gals I use. These are 32V10. That's the largest one available. I don't think I would have needed that, but it gives you maximum flexibility when you want to do things. The two 73s are the latches, the 8-bit latches, and then of course the RAM chip. The resistor array, in hindsight I might have chosen a different one, is 10 times 1 kilobyte of 1 kilo ohm of resistance. 10 times 10 resistors in one array gives you an 11-pin socket. 11 pin is not the problem, but finding these arrays with 10 resistors instead of 8 is a bit of a challenge. So they can be bought, they are a little bit more expensive. So I would have needed only 8 for the data lines, but I had 10 LEDs, so I wanted to have 10. Of course, if you don't have them, you can take 5 resistors array and then put them next to each other and then make one ground connection extra, which will also. The board layout looks very much like the schematic, of course. The Z80 page memory, one gal, and that's another one, and then the buffers close to the slot connector. And these two are the LED arrays with at the bottom some explanation about the signals that you're looking at. So this will show you the V for the video active, so it will blink as soon as you write something to the screen, for example. And also the page selection LEDs, LEDs are there. A15 as well. And some spare signals over there to be used. Some spare signals on the gals are also brought out. This one over here, so you can reprogram and do something fancy if you want to do it. Of course, the keycard can also, apart from making schematic and making the board, can also render it for you, so it will look nice even if you don't have the board yet. And I took the freedom of putting a huge label on the back because I hate it when I have boards and I cannot tell what the function is or what it was paid for. As you can see on the LEDs, one array is just red LEDs, and the other one is normally used for audio signals, but it was nice grouping, and so I could use it for showing the page, showing the video. Yeah, how do you design a GAL if you have the alternative using dedicated or TTL logic? But for a GAL, it's easy to make. You need tables which says if the signals are like this, the input signals are like this, and I want to have output signals like this. So you need a truth table. And for me, the easiest thing was to put it in Excel, put all the signals in there, make the formulas, which look like this. And they are in these cells collected, so I can change the signals, and then it will give me the results of the combinations. So if I have this kind of for port FF, this is I/O port. So if I select memory I/O and then do anything, nothing should change. The port should not be come active. And also which address is there for the port. Ports are addressed with 8 address lines. So you see A0 up to A7, which is 8 lines. And whatever is, if this is not high, I need the addresses 255, so everything should be high. If these are not high, like this one is 0, then you will never have port FF addressed. It's false. If everything else is 1, then I'm addressing port FE, which is my debugging port. So there, the port FE selection comes true. And if it changes to 1, it will switch. This one will become false, this one will become true. And if anything else is in this address lines, like port 5 or port 0 or whatever, both will become false. If I want to see, for example, the sector address in the floppy controller, which is also an I/O port, that's like port F3 or something, or E3. So, then I can just reprogram the GAL for FE instead of make that into F3, and it will show the sector number on the display, on the LEDs. So that's why I think using GALs is easier, and for me at least nicer to do, than having discrete logic in there. Apart from port select, you also need to have I/O write active and the data gate, which is the gate back to the bus, and of course the reset lines also. So that's what's on this first GAL. And the second one is for the RAM chip enable, which I need for reading and writing the chip. And I also need that for support of mapping it out for page 01 and mapping it out for page 15 and 14. So that's what you see in here. I have 2 columns for the jumpers. I have also one here for the video, so I should take care of my video that I'm not conflicting when writing to upper RAM and the video is also active. And of course, I should only work when I have a memory cycle active and not anything else. From that, you can make the rules. So these are the rules. Here you see a combination of the page lines, L 1, 2, 3, and the address lines and the mapping of the ports. The GAL in itself is a very nice chip. It is 24 pins, simple to use. I/O pins can be defined, so you have to set up which pins you want to use for I/O. Of course, power lines are fixed, but everything else is more or less programmable. In DIL or in the PLCC format, for me, I prefer to use the DIPS format, but it's up to you. Programming tool is also available on the internet. When you Google for WinCouple, you'll find it. It's a free tool. You need a serial number to enter, but it's on the website as well. And there's one drawback: it will not run on a Windows 10 or higher. It will start. You can install it. It will start. As soon as you make changes or try to compile, it will crash. So not very nice. But okay, also for that problem there are solutions, of course. I run Windows XP in a VirtualBox. So VirtualBox software is also free of charge. You can download it, install it. And VirtualBox means you have a computer which you can install, on which you can install your operating system or whatever you want to do. And that's, in this case, I use the VirtualBox to install Windows XP. And in Windows XP, then you can run your VirtualBox, you can make it so that it has access to your local drives, so you don't need special things for it. So if you have WinCouple running on my XP, it will look like this. This is my Windows XP system. You might recognize some of the icons. And the only software running on here is WinCouple. And this is the page which you use to enter all the rules to create the GAL. And it starts with defining the pins. So pin 1 is memory CTC. Pin 2 to 6 are address lines. Pin 7 to 8 are the page select lines. That's the definition you give it. It also means that they are output lines or input lines. So this is all input. Of course, 12 and 24 is ground and power. You cannot redefine. You should not redefine it, but it will not work. So you just put it in as information. Those bits are not used. The read lines, the jumper lines, as you could see on the schematic, the input for the jumper. A jumper for the disable readout signals. It's in there, it's not used now. And then you define your output, which is, as you can see, address line 15, 16, 17, 18. The additional address lines needed for the RAM chip. When this is all correct, no typos in there, I think, you push the compile and it will generate a JAD file, a JDEC file, which is used by the program. And this is a PLD file, which is an ASCII, so you can also make it by hand, make changes without it. Not shown, the scroll bar is not at the top, is the header of this file tells you for which kind of chip it should be compiled. And we can do an awful lot of things. You can also run simulations with your file as well. So this is the PLD code for both the GALs. On the left hand side it's for the page select, on the right hand side for the port select. As you can see, it starts with defining the name of the file, of course, and also the device, the last line in the header. In this case, I use the GAL's 22V10. And then the definitions, input, output, and the logic. And you can use it with this very popular program. Easy to use. And you don't have to erase it, it will erase before you program it itself on this same device. So you select GAL 22V10D, and D depends on the type of GALs that you obtained. You put it in a programmer, you program it, and it's 10 seconds, and then you have your chip. You can use it, can test it, can reprogram it again. How do you get the boards? PCBWay is a nice one. Also you can go for Osage Park here in the US. PCBWay delivers, but it takes like 6 weeks before you get your boards from China to Europe at least. I don't know if it's faster in the US, I don't think so. So it takes a very long time. Osage Park is much faster, especially when you're in the US. Of course, there's no reason to do that. In Europe, I could not find a company. There are many companies that can make boards for you, but not at a reasonable price. I think most way too expensive in Europe. And I've made several boards at PCB where they check your files when you upload them, if they are really working, if there are open traces, for example. They send you a mail like, hey guy, you have open traces on your board. Is this really what you want? Which is, I think, very nice that you get a warning for that. And yes, this was the case, but it really it works. Well, getting the boards, you get them in a double wrapped stack of boards, and then the boards look like this, which is really what you want. And of course, you can measure everything if the correct connections are there. But until now, I've never found problems due to board manufacturing. I create my own problems, but not due to this. A big part. Yeah, then the other thing is, of course, getting the parts for the board. You can get most parts also from Mouser and GK and ABN. In Europe, there are some Polish companies, tvsat.com.pl, which have a very large collection also of these almost vintage ICs, and great service, so it looks very nice. Of course, you can also get a lot of parts from China, either new or repurposed from old boards. That's tricky, so you have to find a good supplier at a decent price. You have to, if the offer is too good to be true, normally you will just get ICs with 20 pins or 22 pins or 24 pins, and you just put on a label that you want, and that's not what you want. I've seen that many times. And but the Mini Pro programmer can also check chips for you. So the buffer chips or the bidirectional chips that I have on my board, you can also put them in there and say, well, this is a 640 or 273. Just test it for me, and it will test it in 1 second, and it's worked all out. This is a screenshot of my last shipment from China. These are Chinese code numbers, whatever it is, and they also double check, and all of the chips I bought from this Chinese supplier work. So I sometimes say the Chinese only make stuff to sell. After it's sold, then it's up to you, it's your problem. It's not entirely true. There are also sources in China that you can trust. But sometimes you will learn, and don't spend too much money on your first buy from a supplier. Configuration and jumpers. Page 0 always starts at the beginning of the memory map. Yes, that's true. Except when the boot ROM is active. So you should take care of that. As some of you know, I wrote also a boot ROM for the Model 2, because when I came up with this idea, I think, well, I need tools to verify that this is really working. And I cannot do it by using a boot disk or the standard boot ROM and boot tools using if RAM is not working. I need RAM to run a program. So I wrote my own monitor ROM, monitor code, which is an EEPROM. And it can copy itself to RAM and still work, and you can modify the monitor if you want. But there's also one function in that monitor ROM which checks memory before it needs any RAM. So if you put it into a Model 2, which has only CPU, video card, that's it, and you boot it, it will show on the screen which pages of memory are it found. So it will display on one line a comma for an empty page and an M for a memory page. And so if you put in a Tandy memory board, it will show you the location. If you put in a Tandy memory board which you have jumpered for page 2 and 3, it will show you have a memory board in there, jumper for page 2 and 3. Just correct the jumper and you can boot your system. The 2 kilobyte memory is already, I mentioned that, that's the video memory. It's skipped when needed. And there's a jumper for disabled page 01 and disabled page 14, 15. And there's a jumper for a disabled RAM output, which is currently not used. But it is visible on one of the LEDs. The debugging. Yeah, you can use a modified GAL because it's easy to reprogram. I also have a GAL with a debugging configuration which doesn't use the RAM, it only uses the ports. I have some additional pin headers so I can select signals and show it or measure it. And they are both on the GAL chips and both on LEDs. And the special boot ROM I mentioned, you can do a memory test even without using any RAM, or it can also, when there is RAM available, it can perform memory tests and show you the content of it. And it has also a port out instruction available, so I can do that. This is the board I use for that. The only thing you need is an EEPROM chip and one extra address lines, because it's a 2 kilobyte EEPROM instead of 4 kilobyte EEPROM instead of 2 kilobyte. It will work also in a Model 2. There's a line you have to attach one wire to, and that will work. And in the Model 12, you have a jumper to select for a 2K or 4K boot ROM. And these are the signals in port FF. You can see page and bank select, 40 or 80 character mode for the video, real-time clock interrupt, blank video, and video enable. So this one, well, actually all 8 are visible on the board. So if you switch from 80 to 40 characters, one of the LEDs will go out, turn off. Yeah, before testing the board, of course I did not do that myself, but you will find out the hard way. Double check soldering on bad contacts. And of course I had bad contacts which I found out later, and then you have to fix it. Check for unwanted shorts, especially when you cut wires and they fall on the board and you don't remove them. So have some fun. And check the orientation of your chips. The LED bars, they have almost no indication, so you have to use a multimeter to check the orientation of the LEDs and then put them in, and if you don't, then you have no light. And of course, check the orientation of the board. On the board I wrote which is component side, which is, so you can look at the other cards, but which is up, which is down, still. You can make a mistake because there's no slot, no mechanical preventing, nothing mechanical preventing you from inserting the control. Testing the board. Some of you might recognize this yellow board. It's very nice to have. It's an extender board, so you can put it in the machine, so in the back plane, put the board on top and then run it. What you can see now on the display on the FE port, which has the red LEDs, it's like 5.5. Put out FE 5.5, and it will show this. And the green line is, I think, page 0 active. This is the display of my boot ROM. It says E1 no RAM, which is an error message. But there is no RAM available in page 0. And on top you see 16 characters, 2 commas and 12 M's, and again 2 commas, which means that page 0, 1, 14 and 15 are not available for memory. So I either put in the memory board there or I remove the jumper and it will work. And this is my memory test page, which does not show anything for page 0, but this is all memory field, and there's a jumper for the hard disk controller that maps out memory in this high region. So OE/OF for HD board. You can either use the memory on the HD board, hard disk controller board, or disable it and then run full memory. These 3 columns here show original content, content written, and content read back. So that's the memory, very simple memory test for the board. And what you will also see here, when you give it memory, is that there is no full decoding for those high pages on the hard disk board. So it says OE/OF, actually those are the same. So if you write here, you also change it here. You can see that in the content. Yeah, further developments. I have still a problem in the gals. If somebody finds it before me, then please let me know, otherwise I will just update the documentation on the website. Where bank 01 does not correctly blend out when I disable it. Also the read signal for the data is not fully implemented. I would like to do that. I might create an interface for a thread on the board, and I'm thinking about creating a memory mapped keyboard hole. So I can use a Model 1 keyboard or something that behaves like a Model 1 keyboard, and then run Model 1 games on Model 2. Really. One of the things I already did was change the character set, so I have a Model 1 character set on Model 2 if I want to. Another project on my list is creating interface for an IDE solid state drive. So not an SD card, but really an IDE drive. And maybe put some prototyping room on the card. Currently, as you can see, the card is full, but not cramped. I mean, there's still room on the card. You pay by the square inch and having cards made. Now, the second port is FE. Can be used for anything else, so E5 for a track register or a sector register, whatever you want. I could make that selectable by a switch, which is read out by the GAL. Currently, you would need to reprogram the chip. And more suggestions to come. Questions? Oh yeah, and by the way, this is a link to a page where I put up my schematic and my GAL files, PLD and the JD files. Yes.
So I've developed a 512K module for Commodore Amiga computers, so I'm familiar with the challenges. So great job on the talk and on overcoming all of those. Whenever you first developed it, did you start on like a solderless proto board, or did you go straight to PCB with your design, or what did it look like before the PCB?
Yeah, interesting question. I consider that making a solderless board on a prototype thing. Well, I'm not going to do that, especially using the 80-pin socket is not nice. So I used more than a year to make my board design and go over it again, go over it again, go over it again. So I went and sent it out for manufacturing. You pay like $25 for the prototype, and it came back, and it was first time right. Yes, it was first time right, but it took me over 1 year to do the debugging on paper. And first time right means the hardware was correct, my GALs were not correct, of course. You need to make changes there. But that's much easier than having a board made.
Yeah, I mean, for what it's worth, I took the solderless board route and I got it working like mostly reliable, but of course there's signal integrity issues, and then I would have like one bit that would be flipped at a 16 or something, right? And then it's like, okay, is it the connection? Is it the wire? Is it you know, so forth? But yeah, I mean, it seems like it's so cheap to have these PCBs created that even if you have to spin multiple boards up, it's really not too bad. And I should have, in retrospect, I should have gone to PCB earlier with the prototypes and not spend so much time worrying about basically ghost issues that in the final version aren't going to be there anyways.
Yeah.
Thank you.
Ruud, question. What would we do with this if we went to your site and built one of these? Like, what's it? Is there some use? Like, is it Xenix only thing, or can it be used?
No, it's not the Xenix only thing.
What would you do?
Yeah, it is the main target is giving your Z80 512K of RAM available, which would be very beneficial if you run CPM with bank switching. Could you use it in a Linux environment? Yes, you might. You could use it as a RAM disk for example. But you need, I don't think there's software available for it right now, but you could do it.
Is there a CPM that works with it? Pickles and trout or ones you use?
Yes, I think there are pickles and trout would be. I have not tested it.
Ah.
I have to. That's the question.
What do you use it for?
For me, the fun was in designing the board, building the board, and see that it works. And actually, that's normally the end of the challenge. And now I will, of course, continue and I'll modify my boot ROM in such a way that I can use it and can run, for example, CPM. But the major challenge was come up with a working board. I mean, there's some people here that recognize that as the main challenge.
It's the journey, not the
That's the
destination.
journey. Yes, it's the journey that counts.
VisiCalc. VisiCalc uses
Did I?
it. Model 2 VisiCalc? Who's the expert?
Said Model 2 VisiCalc program can make use of the instrument.
Yeah, it can use it. Yes, that's true.
What would be the approximate cost of building the board?
Easy question, difficult answer. Parts, the board itself is like $20 bare board. Components, depending on where you buy it, $20, maybe $30. So $50 would be what you have to spend on hardware.
Was this your first foray into using gals? Do you have previous experience with that? What's it like trying to move from discrete logic to?
Well, my little board, which has a different boot ROM, uses scale as well, but it's a very simple implementation. But I will do more with the gals because they are very powerful. And I will, one of the things I would like to look into is the clocking mechanisms that you can use in the gals. But this is actually pretty straightforward logic.
Does the gal programming look like Verilog in some sense? Or is it its own unique thing?
Gal programming is common. Win couple is a very nice, easy to use tool. And the cheap programmer that I showed from China, which is like $40, can do it. Cannot handle every gal because it's sometimes specific, or you get fake gals, which also you cannot program. But it's easy to do. It's like programming in EEPROM.
It's way simpler than Verilog.
Isn't couple itself a language?
Yeah.
Verilog, where you have like clocked processes and multiple, you don't have that. I mean, it's
like
a
you
series
have
of
a-
assignments where you just have pins connected with Boolean logic. So you say this output pin equals the input pin and or not this. That makes up the bulk of it. But if you look at the couple manual, which is actually pretty extensive, it can do a lot of things. But for most typical applications, no, it's simple assignments.
It's a lot, it's overkill.
Yeah.
Yeah, but the part you want to use is quite easy to work with, quite easy to understand. Okay, then I thank you for your attention.